Hello, my students. So, today we're going to continue with our intermolecular forces. Last video, we looked at the specific intermolecular forces and what controls their strength. Today, in this video, we are going to look at what are the byproducts of those intermolecular forces. What properties do these start to give our our molecules? So, one of the first things we'll need to talk about is the idea of adhesion versus cohesion. The intermolecular attractive forces can either cause a molecule to adhere to a new surface, or they could stick together, molecule A onto molecule A. So we have two different properties on whether they interact with other like surfaces, and one of whether they all should interact with each other, but it's whether they interact with other surfaces. So cohesion is the ability to stick together. A cohesive team sticks together. So adhesion is the ability to stick to another surface. Often it's thought of as solid to liquid or solid to another solid. Adhere to a surface. Now, in order for any sort of adhesion to occur, the two surfaces need to have similar polarity. So they need to have similar intermolecular attractive forces. And these will go on to explain a lot of three big properties of liquids. But you can see on the right, the rose petal. Roses have a waxy coating on the petals. So these waxy coatings are essentially organic, nonpolar surfaces, like London dispersion forces. Water, because it has a strong cohesive force, will form up into little droplets. They are going to try to minimize the surface contact with the rose petal. So it's going to bubble up. So you're going to have as minimal amounts of water touching the surface of the rose as possible. So it's going to bind tightly together. And so that's why we have these droplets appearing on the rose. Now, if you have a surface that has good adhesion to the water would, since the bubble would collapse, and it would spread out in a puddle. But so you'll notice that, like most floors, you get a puddle, but if you have freshly waxed a floor, you're going to have water droplets forming. This is also partially why we see different types of meniscuses on the surface of our test tubes. We see meniscus because the glass is not just it's not just sand, it's a silicon dioxide where there's oxygen molecules sticking out from the surface of the glass. And so the water molecules would gladly interact with the surface of the glass. So it's going to adhere to the surface, and that's going to cause it to creep up the sides of the glass. And that's why we have a dipping meniscus, or a concave meniscus, because the water is trying to essentially climb the walls to get extra adherence. But if we were to fill a test tube with mercury with its metallic bonds doesn't really want to interact with the surface of the glass, and so it's going to try to push itself away from the glass. And so it's going to create a convex meniscus. It's going to try to maximize its distance from the glass. Now, what creates a deeper meniscus, either positive or negative, has to do with the gravity and the surface area that is created by the width, and essentially the diameter of the test tube. But one of the first major properties is viscosity. Viscosity is the measurement of the speed of which a liquid flows. How easily does a liquid flow when you try to pour it? Certain liquids are very viscous. Certain liquids are not very viscous. Syrup, glycerol are very viscous, especially when they're cold. You try to pour them, they're going to pour very slowly. They're going to flow slowly. Ketchup could be considered viscous, that it doesn't just naturally pour out. A lot of our condiments would be considered viscous, especially after shaking them. Now, things like hydrocarbons and even water are not usually considered very viscous, and so those will flow rather easily. But this is essentially a case of extreme cohesion that allows a liquid to act similar to a solid. But since the intermolecular attractive forces are always opposed by kinetic energy, anything that gives the liquid more kinetic energy means viscosity will decrease. So if you increase the temperature, by similarity, viscosity will decrease. You put syrup in the fridge, it's going to pour more slowly. You microwave some syrup, you get hot syrup, it's going to pour very quickly. That's kind of silly property. We don't usually measure that too much, but there are some things you can do with that. Another property is surface tension. This is the case of cohesion when applied to a boundary, such as another solid, a liquid, or a gas. So the most common surface tension is the surface tension we see when water is open to the air. That you can float things on the water based on surface tension alone. Things that would normally sink, that have a higher density than water, if you keep the surface tension intact, will float. The idea here is that when you have water molecules not at the boundary, they're seeing attractive forces from all directions, and so they're really kind of seeing they're kind of seeing like they're not really pulled in any one direction. But when they're in the boundary, they're seeing a whole region where there's not any attractive forces. So we are seeing no forces. You're seeing attractive forces in all directions except for up. Now, when you see the something pushing downwards, equal and opposite force, the water is going to push backwards in order to avoid breaking all of its new bonds that it has with its friends. Now, the atom in the middle doesn't really care whether it gets pushed down or up because it has more bonds here and there, so even if it loses a bond from up top, it's getting new bonds down below. But the atom on the surface needs to stay in place. And so as long as the force is not stronger than the surface tension, it remains intact. So these small little water bugs, which typically have like a non-polar hydrocarbon-based foot pad, can push down against the water. They weigh so little and they have such a large surface area that you can spread the weight very well. They can float on the water. They dimple the water where they're stepping, but it's able to withstand that, and they can walk on water essentially. But you can do this just with simple water. You can essentially, you may have seen some videos. I know I've seen some, and they even had a game of this in like JoJo's Bizarre Adventure, where you're testing how much water you can add to a glass without it overflowing. And the idea is that you get more and more and more. A drip, a drop, and it starts to overflow the brim. It's higher up than the lip of the water, or than the lip of the glass, because the surface tension allows it to bubble up like that, and it's still keeping the surface tension, but eventually you get so much strain trying to pull the water out because of gravity that it will break the surface tension and then the water spills. But until that point, you can keep adding water and get it further and further. You can get it noticeably like several centimeters above the rim of your glass, especially depending on what diameter of glass you have. It's a fun example to show to kindergartners. It's like magic. And the third major thing is capillary action. And this is another example of adhesion versus cohesion. It's the ability of liquids to move upwards against gravity, given narrow tubes. The idea is that as a liquid adheres to the surface of the tube, it will increase the surface area of the liquid, and so the meniscus will dip down further. Now, surface tension, by its very nature, wants to minimize the surface area on this air boundary. So it's going to start to pull the liquid up the tube. So instead of having a dipping meniscus, it's going to bring that up. And that's going to, of course, further allow the liquid to creep up the tube a little bit more. And so we see that a liquid based on the diameter of the tube will creep up higher and higher due to increasing capillary action. Now, this is part of the reason how trees can move water from roots to leaves, but there's some other things in effect. This is not the sole reason, but it is a way to assist in this. Now, you can see a little bit on the picture to the right, the wide tube has liquid there, and as we get narrower and narrower, it's going higher and higher up the tube. So, one of the things we'll have to deal with in this chapter is phase changes. We're talking about going from liquid to solid, solid to liquid, liquid to gas, gas to liquid, and even solid to gas and gas back to solid. Right? When we dealt with enthalpy, we only looked at the relationship between the heating and cooling of substances. But there's actually a enthalpy that we can deal with when we go from these boiling and freezing and melting and condensing. That we can look at these as enthalpy of fusion and enthalpy of vaporization. That there's an energy associated with these phase changes. Of course, the sign of the enthalpy will relate directly to the direction of the change. But this is often given as a kilojoules per gram or kilojoules per mole. That typically thinking, melting process is a positive enthalpy, boiling process is a positive enthalpy. It takes energy to melt. It may not look like it takes energy to melt, but you put energy in to melt a substance. You definitely know you put energy in to boil a substance. So the opposite must be true. When you freeze something, you take energy out. When you condense something, you take energy out. So we could also undergo a sublimation, which is a process by which a solid goes directly to a gas phase without passing through a liquid phase. And the energy associated with that is just simply the sum of the two separate enthalpies. So let's look at this. One thing we can learn, and one thing we will do, is learn how to use graphs and read graphs in these upcoming chapters. We'll be using a lot more charts, and there's a lot more math. But essentially, we can look at a heating curve. If we combine our idea of Q equals mc delta T with our enthalpies of fusion and vaporization, we can get this heating curve. It relates two terms: the x-axis, which is heat added, and the y-axis is the temperature of the substance. With that in mind, we can break this down into 5 distinct regions. We have first the heating of a solid, which is with its own distinct specific heat capacity, C. We have the melting of that solid, which is our enthalpy of vaporization. We have the heating of the liquid with its own distinct specific heat capacity. This is usually one of the larger portions. The vaporization of the liquid and the heating of the gas with its own specific energy. So you'll note that in regions 1, 3, and 5, it's just a simple Q equals MCAT. They all have their own distinct C. But the slope of this line is directly proportional to the C. So the slope of this is going to be essentially the C, the M times C. Because we're looking at the change of T with heat. Also note in regions 2 and 4 where melting and boiling point occurs that typically during these phase changes temperature does not change. When you're melting ice, the ice stays at 0 degrees until it's fully melted. So when you put ice into your liquid, and so you put ice in a soda, you're trying to chill the soda down to 0 while the ice slowly melts. The ice takes the energy and it keeps things frosty cold while it's melting. The same thing when you're boiling a liquid. Until you completely boil your water, the water stays at 100 degrees. So once you get something to a vigorous boil, oftentimes they tell you to turn it down to low, because you don't need to boil it to dryness. You just want it to stay at 100 degrees. So that's something to keep in mind. So let's do a quick calculation. How much energy would it take to fully boil 20 grams of water stored at 25 degrees C? So 20 grams of water. So water, 25 degrees C. We have a C of 4.184 and a delta H vaporization of 40.66. I'm writing those down real quick, and now we'll go to our document camera. So, we're going to break this down into 2 steps. I could have broken this down into a lot more steps, but we'll leave it just 2 steps. Step 1 is heat the water to 100 degrees. Step 2 is going to be boil the water. So with that in mind, breaking down in those 2 steps. So at 25 degrees, we need to go to 100 degrees. So our Q of this situation is 20 grams. Our C, which is our specific heat capacity of water, is 4.184 joules per gram degree C. And our delta T is 100 minus 25 degrees C. So 75 degrees C. Doing that first step. So 20 times 4.184 times 75 gives me 6,276 joules. If I divide that by 1,000, I get 6.276 kilojoules of energy. Now, part 2, our enthalpy of vaporization is going to be the moles times our energy, 40.66 kilojoules per mole. Well, how many moles are in 20 grams? 20 grams. Water, H2O, 1 times 2 plus 16. And where do I get these numbers? As always, the periodic table. Grams per 1 mole. This gives me 20 divided by 18 is 1.11 moles. So I'm typing 1.11 moles. There's our N. And that's going to cancel moles, and that's going to give me just units of kilojoules. So 1.11 times 40.66. Crap. So we get 45.17 repeating kilojoules. Now, the total energy is going to be the enthalpy of heating plus the enthalpy of vaporization. So when we add these two together, 0.276, we will get the total energy of 51.45. I will say 454 kilojoules. That's how much energy is going to be needed to boil 25, completely boil 25 grams, 20 grams of water. That is normally at room temperature. So, and as you see, here's the work. I rounded in a couple places. That's why it's not quite the same, but it's essentially the same. Now, with that in mind, that's where I'm stopping this video. Have a good day.